Good morning, everybody. Hereby, I open this academic ceremony in which Daniel de Melo Pereira will defend the academic thesis, Biomineralized Collagen for Bone Regeneration, Insight into the Cell Material Interactions. May I invite you to present a summary of your study and the conclusions for your thesis.
Dear Prorector, dear members of the committee, my friends and family, I will now start my presentation. I would like to tell you the story of how was it that I ended up researching biomineralized collagen for bone regeneration. And to do that, I will start with a few concepts. We will start with biomineralization. How does it relate to biomaterials and bone regeneration? And how these three concepts come together into the actual experiments I did in the lab. So, of course, I will also show you my key findings, and I will finish this presentation with a brief summary and an evaluation of its impact. This project was born out of my fascination for biomineralization and the structures it produces. Biomineralization are the mechanisms, the processes by which living organisms are able to control mineral deposition to form complex, intricate structures that serve some purpose for these living organisms. I brought you here some of my favorite examples. These are coccolithophores. They are unicellular algae, and they produce these beautiful calcium carbonate shells. Very similar, also unicellular algae diatoms, they produce silica shells. So these are basically glass sculptures. And an example that I think everybody here is familiar with, the stinging nettle, which, as you know, as you brush past it, it burns you. And it does that because when you touch this calcium phosphate silica spike, you break the tip, and it's actually an hypodermic needle that injects toxins into your skin. That's why it burns so much. There are many other examples of biomineralizing organisms with other mineral systems, systems other than calcium carbonate, calcium phosphate, and silica, although these are the main ones. But we will now focus on our own vertebrate skeleton. And we have here a schematic of a skeleton and a zoom in into the inner structure of a bone. And what I would like you to remember from here is its composition. It's made up of 65% calcium phosphate, hydroxyapatite is the name of the mineral, and 25% organic content, out of which the majority is collagen. 90% of this organic content is collagen and 10% water. Not only the composition is important, but also the structure, and in particular, how the collagen is organized with the mineral components. The mineral particles are embedded inside the collagen fiber, and this is in part a reason for its very strong toughness and other mechanical properties. Now, critically, this structure of embedded mineral particles within the collagen fibers, what we call intrafibrillar mineralization, was able to be reproduced in the lab by an ingenious process. And this was actually the topic of my review chapter. To what extent does biomineralized collagen replicate the native structure of bone? What challenges remain in bringing it closer to our native tissue? And one of my main conclusions was that there are not that many preliminary studies um, looking for applications of this material for bone regeneration. And I think that this material stands a good as a good candidate for bone regeneration applications, because there's actually a need for synthetic alternatives to bone transplants in certain clinical situations. For example, in maxillofacial reconstruction, spinal fusion, large and complex fractures, tumors, or infections, you need a bone transplant that has associated drawbacks. There's a limited availability of these transplants. There's the risk of complications of the surgery to obtain the bone transplant, and also a risk of rejection by immune reaction. Now, okay, we have this biomaterial. How do we evaluate its potential for a bone graft substitute to replace a bone transplant? There are many things that come together to make sure that the biomaterial works as an implant. One of them in bone is its capacity to bind directly to the bone tissue without the formation of a fibrous capsule around it. What I have here is an illustration, an image of a calcium phosphate implant in black, and it's surrounded by bone tissue in pink. And you can see that there's nothing in between. There's no fibrous capsule formation. We call this osteointegration, or a good example of osteointegration, and is absolutely necessary for this implant to be gradually replaced by the bone tissue so that this gap is eventually fully healed. Um, how can we predict osteointegration with in vitro experiments alone? Probably we cannot, but we can do some experiments that at least point us in the right direction. There's a physiological mechanism of bone remodeling, which is the mechanism by which our bones maintain their healthy status throughout our lifetime. Like any other tissue, um, the old tissue needs to be removed and it needs to be replaced by a new one. And this is done by specialized cells. We have osteoclasts that resorb old bone and osteoblasts that form new bone. And this is very similar to what we want to happen to our biomaterial. We want it to be gradually replaced by the native tissue. And it was then that the first question that I wanted an answer to became obvious to me. Can osteoclasts resorb biomineralized collagen? So I went into the lab. I prepared some biomineralized membranes for cell culture. You can see them here, mineralized and unmineralized. And I used some human osteoclasts and did cell culture on these membranes. Here you have some images of my cells. I will guide you through it. This one here in the bottom is an osteoclast. We know it because it's a large cell. It has multiple nuclei, and it has this green signal coming from it, which is from TRAP, which is an enzyme specific for osteoclasts. And here you can see the morphology of the cell a little bit better in scanning electron microscopy. So osteoclasts were forming, their morphology was good, but there was no evidence for resorption. So in my next experiment, I decided to introduce some modifications on my biomineralized membrane. I added cobalt ions because it has been shown that cobalt in some amounts potentiates osteoclast resorption, and some extra mineral content. And we saw that there was a gradual release of cobalt from the membranes along time. There was about 4% increased mineral content in weight that then made our membrane a little bit stiff, well, 10 times stiffer. We again did cell culture on these membranes with osteoclasts, and this time we did see some evidence of resorption. So I'll guide you through it again. So in the center you have a cell, it's a large cell that has many nuclei inside. It has this green signal again, so we know it's an osteoclast. But it has also a structure that we didn't see before. This bright red circle, what we call it's an actin ring, and it's part of the cellular machinery to resorb the substrate. When we removed the cells from our membrane, we saw that there were cavities left that resemble resorption peaks, and they were also corresponding in size to these actin rings we saw in the fluorescence microscopy. Another piece of evidence came from the quantity of calcium in medium. So if osteoclasts are resorbing calcium phosphate, they have all this extra calcium within them, and they secrete it via vesicles to the medium, which you can then measure. So if you see at day 9 and day 16, we saw a difference from our control, which indicated extra calcium. So the overall conclusion was that osteoclasts are able to resorb this modified collagen biomineralized membrane. Now, the other side of the story is, of course, bone formation. And what I looked at was, can this material, can biomineralized collagen direct the indifferentiated cells that have the potential to become bone-forming cells? So they have the potential to become matrix-producing osteoblasts, and eventually they can form new bone. If they are in an undifferentiated state and they are in contact with biomineralized collagen, are they directed towards this differentiation pathway, and to what extent? So I did cell culture of these undifferentiated precursors on the biomineralized membrane, and I looked at gene expression of known osteogenic markers, and there was some evidence of osteogenic differentiation. I brought you a couple of examples here. We have 2 early markers of osteogenesis, RUNX2 and Osteoponte, that they are early markers, so they're supposed to be upregulated at an earlier time point, and that's what we found on our biomineralized collagen membranes at day 3. Another 2 interesting genes or interesting results from these genes are ENPP1, which inhibits mineralization, and we found it expressed early on, which then fell down to 14 days. And we had collagen 1. If you recall, collagen was the main component of the organic fraction of bone, and we found it expressed, more highly expressed at day 14. So these 2 together seem to indicate that, at least from day 14, there might be a commitment of the cells to start producing matrix. So the overall conclusion from this chapter was that there is indeed some evidence that these biomineralized membranes are able to direct these undifferentiated cells towards an osteogenic lineage. We arrive now at the end of my talk. I would just like you to take home the take-home message. Very brief summary is that this biomineralized collagen can undergo resorption by osteoclasts, but there is some influence of the substrate into undifferentiated cells, directing them into an osteogenic lineage. And I'll try now to do an evaluation of the value of this, right? And in 2 parts. So, of course, for the scientific field, for my colleagues, the value comes from the results and the data itself that I think, in my opinion, opens up many interesting pathways for investigation. So there is much research to do. And of course, for society at large, the value also comes from that, because it's only from continued research into new materials, new strategies, that we are able to offer better solutions for patients which have very real problems, like the ones I presented earlier with the large bone defects. I would like to thank my supervisor, Pamela, my co-authors, Maria Jose, Nilofar, Matthias, and Noel, and my students, Luis, Lotte, and John, all my colleagues from Merlin, and you that are in the audience and were able to come here, also the people attending at home. Thank you very much. And I now give the word back to the prorector.
Thank you very much. Thank you very much for your very clear presentation. We will start now with the opposition. And the first person to start this opposition is Dr. Anna Akiva. And she is specialized in biomineralization and working in the Radboud University Medical Center and online with us. And I'm happy that she is online. We can all see her, I suppose. Yes. And I give the word to you.
Thank you. Geachte promovendus, dear Daniel. First, congratulations with this nice thesis. With great pleasure, I read your thesis. You demonstrated critical thinking on creating a complete remodeled material for bone regeneration while being inspired by nature, diving into the literature of both bone structure and bone mineralization, which is, as you know, my favorite. You beautifully used many chemical and analytical techniques to characterize the quality of your material, side by side with cell culture studies to study the functionality of the material you created. So again, congratulations. Now, before we dive into the chapters, I would like to start with the very first sentence of your thesis, actually with the title of your thesis. You write that you are studying biomineralized collagen for bone regeneration. So my first question is, how would you define biomineralization?
Thank you for your very kind words about my thesis. Can you hear me well?
Yeah, now it is.
Very good. And for your kind words for my thesis and for your interesting question. And so the way I define biomineralized collagen is the material I produced in the lab. So collagen type 1 showing the native banding that was mineralized via the PILP method. And so it shows intrafibrillar mineral, the same way that is found in our native bone. So with crystallites of hydroxyapatite oriented along the long axis of the fibril and with a high content of mineral as well within the fibril. But
it's not what you said 2 minutes ago. And I will help you. So yesterday I also opened the On Biomineralization book of Steve Weiner and Heinz Lowenstein, and they opened their book by saying biomineralization refers to the process by which organisms produce mineral. So, who is the organism?
Apologies, I just defined biomineralized collagen instead of biomineralization. No, indeed. So biomineralization are the processes by which living organisms are able to control mineral deposition to form structures that serve some purpose for these organisms across all kingdoms. Yeah, that's the same definition.
Yeah, so I think that maybe it's, well, the way I see it, a little bit maybe misleading to call your collagen biomineralized collagen. I agree that you have mineral, but we'll speak about it in a second. And you have, of course, the collagen type 1 and so on, but it is not biologically controlled, right? The PILP is not biological element. So maybe you can find a better terminology instead of biomineralized collagen.
Perhaps. So it was simply to avoid calling it every time collagen with intrafibrillar mineral, which is a mouthful. So I just opted for biomineralized collagen. But of course, if you define biomineralization as minerals being deposited by living organisms, and then I call biomineralized collagen the material I produced in lab just by pipetting, then it's not biomineralized.
Maybe
perhaps a better name for it.
Maybe a better definition would be just biomimetic or bio-inspired collagen mineralization, and then I think it would have been more accurate.
Yes, if I can just reply a little bit to that. So there's in literature, the words bio-inspired and biomimetic have been used since calcium phosphates are in use, right? So that's for decades now. And whenever you use them, you, of course, in the context, you need to specify in your paper, in the thesis, what does it mean, right? Biomimetic. And that's the reason why I opted for biomineralization, but biomineralized collagen, I should say. But it does have that caveat of, indeed, it's not a living organism producing it. So, yeah, thank you.
Okay, so let's take it another step. I'm jumping a bit, but indeed, so you mineralize your collagen with PILP, but at least for me, this mineralized collagen is in two ways different from real biomineralized collagen made by bone, both in composition and in morphology. can you think what are these two differences? I think that actually you mentioned them, but what are these two differences when you compare it to natural bone?
Yeah, exactly. So there are two major differences in composition and chemistry. And I will talk first, so I will specify them for different length scales. Biomineralized collagen or biomimetic collagen, as I have here, at a very small scale of 1 fibril, has its best replicability of the native tissue. But even there are differences, of course. For example, it's lacking other non-collagenous proteins that are found in bone. For example, osteopontin, osteocalcin. And it also, the mineral itself, it's lacking, for example, trace ions within it. Our bone apatite has many substitutions which are not present in my material. As you go up in scales, so going from tens of microns to hundreds of microns, what you start lacking is more the structure, the hierarchical structure of bone, where you have fiber bundles and then lamella of parallel fibers, and eventually the large Versian channels and osteons of cortical bone, and the lamellar structure of cancellous bone. So that is also, of course, missing in this material.
That is correct, but I was actually referring to the level of the single collagen fibril, and maybe I will help you a bit. The first thing, you cited the science paper of Natalie Reznikov. And Reznikov showed quite nicely the collagen fibril and how the mineral is arranged inside, but it wasn't the only thing, right? She actually also showed something in addition.
Yes, so there was an amount of extrafibrillar mineral as well. And they were not in the shape that you would expect them to have in the platelet shape that it normally has been described in literature so far. They have these curved minerals, which I don't think we have, of course, in my material as well, if that's what you
so this is indeed one point, and I think it's quite important, especially for your study, because my feeling is that the cobalt that will come later kind of replace this extrafibrillar mineralization. Basically to have this mineral that's lining outside of the fibril and maybe helps also with the resorption later on of the collagen, or mineral and collagen.
Our goal, apologies, what?
No, I'm saying indeed that maybe it replaced. The second thing is and you mentioned it briefly, but the mineral is not, we all get it wrong, but it's actually the mineral of bone is not hydroxyapatite, right? It's, what is it?
Well, you can call it bone apatite, you can call it carbonated, poorly crystalline apatite.
Carbonated
Yes.
hydroxyapatite, and it's really important.
Yeah, it's its main substitution, it's carbonate, for sure.
And why is that?
I think it's what grants it its poorly crystalline character, which would then influence all of its properties, including, for example, dissolution, resorption, probably as well. I would say, yeah.
Indeed, I think that well, basically it will increase the solubility. So hydroxyapatite is one of the most stable minerals in nature, right? While the carbonated hydroxyapatite can be much easier resolved. And then again, if you speak about, well, this is what you want to achieve at the end, right? Material that will be strong as bone, but will also have the capacity to resolve relatively easily. So maybe these two will or could have helped you with the thesis. I mean, with what you wanted to achieve.
Dr. Akiva, I need to interrupt in this very interesting discussion. Sorry for that, but the time has passed and we need to go on to the next examiner. So I apologize, but maybe at the end, if there's no time, we will come back to your point and get to the nitty-gritty of it. But I would like to give the word to the next opponent, which is Dr. Gunnar Zeider, and he's the chair of the Assembly Committee. And Dr. Gunnar Zeider is an expert in polymer engineering here at the Maastricht University. Dr. Zeider, the word is yours.
Please use your microphone.
Sorry. Congratulations to your nice thesis. Nice to meet you in person here. Yeah, as explained, I am a fiber guy, a polymer processing guy, not a biologist. And when I saw your nice pictures of your fiber structures, for example, on page 132, I thought, hey, we are doing so much to produce fibers by machines, and here's so nice fiber structures. And it seems to be relatively easy to get these membranes. Could you explain a bit how they are produced, how they are generated, how they are assembled?
My highly esteemed opponent, thank you for your kind words for my thesis and for your question. I had some help producing these fibers. So these are collagen fibers. So the process by which they self-assemble has been evolved over some hundreds of thousands of years. So that's my help. I only had to put them together and in the right conditions. So you form collagen 1 fibers in their native state. So showing the debanding that is maybe even visible in this image by giving it the right conditions. So pH 7.4, some ionic content in solution, and also the presence of a phosphate buffer helps. And that was it. After some optimization, we were able to obtain them. Yes.
I heard about that. Okay. And if you could wish, what would be an ideal structure? So yeah, what is the ideal membrane for your goals?
Yes, that's a very interesting question because it ties in with also what Dr. Akiva mentioned, which is what is lacking in this material to bring it closer to the bone structure. And one of the things, it's the organization of these fibers, for example. They are now randomly oriented, but in bone, it's not so. So they're grouped in fiber bundles, in lamellas, and more complex structures. I would say that the first step would be to obtain a matrix that is made up of parallel fibers, which then this would be a nice building block to build other structures with it.
Mm-hmm. Do you have ideas about the processing options, maybe electrospinning with giving orientation or something else?
Also, a very good question. I've thought a little bit about it. I've read the literature. So the problem with this type of collagen is that we cannot steer too far away from those conditions I mentioned before. So pH 7.4, temperature 37 degrees, and these ionic contents. And electrospinning uses a lot of solvents that are not compatible with these conditions. There are other techniques that could work and have been shown to work, to produce aligned collagen fibers with the banding that are required for the next mineralization step. For example, wet spinning is one of them. I'm just not sure if you could scale that to the production necessary to form large constructs.
What could be the problem?
What could be the problem of wet spinning? I'm not well. Solvent compatibility, we need to solve that in that particular case. But it's again the conditions that they need to be maintained in that order. So the conditions I mentioned before, until at least you cross-link the collagen, and then it's more amenable for handling, for manipulation. Yeah.
Okay, thank you. I learned that stiffness and elasticity plays a role, and that is important as a characteristic of your membranes. Can that be engineered or influenced? I mean, as a polymer guy, I would choose different, maybe molecular weights, E moduluses, or whatever. Can that be done in your case too?
Yes, so stiffness. So we saw, for example, in chapter, in the cobalt chapter, we saw that by adding extra mineral, we were able to increase the stiffness by 10 times. But there are other ways as well. Already by orienting the collagen fibers, you reduce the porosity of the membrane, and that would help increase its stiffness as well. So stiffness is interesting by itself alone, but but the more interesting thing to me is because you can have a very stiff material, but very porous as well. But for osteoclasts in particular, they like to be able to seal an area of a surface very easily, and all these pores in the surface don't really help that. So there is a compromise somewhere between stiffness and surface porosity that would allow osteoclasts to better resorb this material.
Thank you. In your presentation, I saw that nice picture of collagen and the interfibular hydroapatite. And there are similar structures in technology, for example, carbon reinforced parts. There you have a polymer matrix and reinforcement in that matrix. But in technological applications, there is an adhesive in between the fibers and the matrix. How is that here? How are they connected?
Excellent question. The really short answer is that I'm not sure, but I'll try to hypothesize. So in bone, let's go back to the native tissue. In bone, as we mentioned already before, there are a lot of other proteins, non-collagenous proteins, that are probably interfacing between the mineral and the collagen itself. In this synthetic material, it could be that it's just electrostatic interaction. So these collagen fibers are mineralized by a liquid-like complex that infiltrates spaces, really the well-defined spaces within the collagen fiber that have some electrostatic character that allow them to do that, to go there and be stable. And when the crystallites are formed, well, they're solid particles, so they just stay there embedded, but there could be some electrostatic interaction with the collagen itself.
Thank you. Another question? Okay. Very short, I promise. Yeah, during your remodeling, I mean, you put something in the human body and then you have this complex interaction that you need. And from an engineering perspective, yeah, that's extremely complicated. Why is it not possible to engineer a material in a lab where you can control your boundary conditions and then put it in? Why do you need that interaction and growing inside the human body? For me as an engineer, that's complicated.
That's a very good question. I'll try to be as brief as possible. So when you implant a material in bone, there are at least 3 mechanisms by which it's degraded. And indeed, if there were no cells, you would have to think about how does it degrade and at what speed the bone is being formed. But I choose to leave that, or try to leave that, to the cells themselves. So I take my hands off the engineering and say, if osteoclasts are taking care of it, then they're probably recruiting osteoblasts that will likely bring in bone after that. Yeah.
Thank you very much.
Thank you very much, Professor Zeider, for your contribution. The opposition will be continued by Professor Janneke Klein-Nuland, and she is chair of the cell biology of bone adaptation and regeneration at the Center of Dentistry in Amsterdam. And we really appreciate having guests from other cities in our university in the opposition, and therefore I look forward to your contribution. The word is yours.
Thank you very much. First of all, I also wish to congratulate you very much with your beautiful thesis. It's a real wonderful accomplishment. And I also wish to congratulate your supervisor, Professor Bibovic, with the, yeah, as I said, the beautiful thesis and also the beautiful cover. Another thing I also appreciate is a little bit your artistic way of thanking people. In fact, I really, really like that. But of course, I have to question you regarding the content of the thesis, and I'd like to continue a little bit where the last opponent stopped, because that is about the in vivo usage of the material you're developing. You know, I am from the dental field where maxillofacial surgeons use bone for reconstruction. Sometimes use skull bone, and sometimes, for example, from the iliac crest. What are you now aiming for to make? Is it more skull-like bone or more bone from the iliac crest? And does it matter for you, for the aim in the end?
My highly esteemed opponent, thank you for your very kind words for my thesis and for your very good question. Far from that still, but so to replicate specific types of bone. But I would say that perhaps the easiest or the first one to be obtained would be something akin to cancellous bone, particulate cancellous bone, which would be then, if you take this material and you make it a little bit more, it needs to be more dense and compact. It's very loose now. It's more similar to woven bone than it is to secondary bone.
Because that is my point, in fact, because skull bone is much more stiff. And since you aimed for different stiffness, or you made your material more stiff, and then I thought that's maybe good if it looks more like skull bone, because it performs better, I think, in vivo. But I'd like to talk a little bit from the in vivo perspective, because you tested osteoclasts, mesenchymal stem cells, their effects on your bone. But if we go now in vivo, where do your osteoclasts come from?
Well, when you implant a material.
Yeah, if you implant the material, where do they then come from?
From the hematopoietic precursor, so monocytes, macrophages that are in contact with the material as you implant it.
Yeah, and one thing is very important is possibly vascularization or not. Can you say something about that? Speculate how important is vascularization in vivo, and did you look at any vascularization markers as well?
I can. So I didn't look into vascularization, despite its big importance, of course. My approach to bone graft substitutes is on the material side. So perhaps to have the characteristics that would allow proper vascularization, which means then porosity and connectivity between that porosity that allows growth of vessels into the material. But I did not look at any expression of these angiogenic markers on undifferentiated cells, for example. But it's something that we should definitely look at.
Yeah, thank you. So the thing is also, I'm fishing a little bit. Does it matter whether the material is more stiff or less stiff, depending on how much calcium phosphate you put in there, whether it would affect, in the end, the clinical application. I'd like to ask you also about your bone, about your remodeling, because I noticed that you study osteoclasts, and indeed remodeling starts with osteoclastic bone resorption, followed by bone formation by the cells. But is there now somehow a role for the osteocytes? And maybe you need to think from the in vivo perspective, if you put your material now in existing bone, because in my opinion, I thought that bone remodeling was that osteocytes play a role in normal bone in the process of bone remodeling.
Absolutely.
Can you speculate a little bit about the importance of these cells?
I can, yeah. I will try.
Yeah.
So, of course, in vivo, in a normal situation in bone, the signaling for the osteoclast to start removing bone probably comes from osteocytes that are damaged apoptotic and then initiate a signaling cascade that recruits osteoclasts to remove that tissue and then onwards towards osteoblasts. But in a wound healing setting, in a bone regeneration, I struggle to see what the role of osteocytes that are in bone, in the boundaries of the wound, for example, would have. I'm not entirely sure what it would be. And I decided then to focus on the other two that have known roles. So the osteoclasts for resorption of the material in this case, and then the recruitment of undifferentiated cells that would then become matrix-producing osteoblasts.
Thank you very much. I think I agree with you, but I think they might signal, you know, they might produce based on mechanical loading situation on the bone, perhaps produce signaling molecules thereby affecting the cells you have studied. I don't know whether my time is over already. Do I still have time for a question? Okay, so yeah, the influence of cell types on each other is quite important, I think. So but did you consider, you have, yeah, I consider what you did is a little bit of a model for me, you know. What happens if you load your material and the cells on there? Would you get similar results or would it change everything?
If you mechanically load the material, yeah. It's a very good question. So also one thing that you can do with this material, it starts out as a gel, which is then compacted. So it is relatively easy to embed cells within the material, so make sort of an osteocyte model, so to say, and then mechanically stimulate that substrate and look at what the cells are then, how are they behaving? Is there any expression of any markers that are of interest?
So do you think that's the future then?
Yes. I think that for applications in vivo, so for bone regeneration, I think it makes sense to look at what currently works best. And as you said, what works best is bone. So then producing materials that somehow are inspired by it or replicate its key features seems to be, to me at least, one option worth pursuing, to put it this way.
Thank you very much. I'd like to give the word back to the rector.
Thank you very much, Professor Klein, for your contribution.
Thank you very much for your contribution to this defense. I would like to continue the opposition with Professor Martijn van Greenstein. He's the secretary of today's committee, and the word is for him. Oh, by the way, I forgot to mention that he works here in Maastricht University, specialist in regenerative medicine, and in the Institute of Merlin. Please.
Thank you, Pro-Rector. Daniel, muchas parabéns for the very nice thesis. I really enjoyed reading it. And of course, also to your promoter. When we look at the thesis, we have heard already quite some of the material. We went a little bit to the in vivo and the cells, and I would like to continue with the cells a little bit. When we go to chapter 4, there the main cell type is actually the osteoclast. And you describe there how your cobalt is actually making osteoblast active. And the question here is it good that they are immediately active? Or would you rather have, when you implant it, that you have like more a timely schedule of that?
My highly esteemed opponent, thank you muito obrigado for your kind words and for your question as well. So in chapter 4, we did use cobalt. We also, if you remember, increased the mineral content of the membrane, so it was stiffer. And in the end, there was some confusion as to whether the resorption that we saw was an effect of cobalt or this extra stiffness components. In my discussion, I go on about it and say that it's probably the stiffness actually. But to get to your point, do we want them to actively, immediately resorb this material in vivo or take a more gradual approach? Probably the more gradual approach in vivo makes complete sense because it needs to hold its shape and be slowly and gradually replaced by native tissue. So you need also the mineralization of it, which we don't know how fast it goes. But in this in vitro experiment, it wasn't so much about of how fast are they activated or how fast do they resorb, but if they are able to do it. Because at this point, I was not sure, because on the previous chapter, we didn't see any resorption. So we were just wondering if it was possible or not.
I was also thinking, because you also mentioned now yourself, there's still some debate. What is actually happening? Is it's the cobalt or is it the stiffness? So how would you try to find that out? Perhaps also when we go back to the second opponent, who also touched a little bit upon that.
Yes. So one of the main limitations of that chapter was that our membrane that was resorbed had both conditions, had both the extrafibrillary mineral and the cobalt. Well, we can make a control that doesn't have cobalt, for example, and we can see if the same happens there, and then we would know for sure. I would like to talk a little bit more about it because I think it's not the cobalt, because at the concentrations that it's released from the substrate, there's no evidence in literature whatsoever that it promotes osteoclast activity. Of course, lack of evidence of absence is not the same thing. So it could be that it has an effect and we would have to test it. But on the other hand, stiffness does have that background. So in some substrates, it's always connected with other things. So with porosity, for example, but it has been shown that stiffer substrates undergo resorption more easily. So that's why I think it was more the stiffness and less the cobalt, but we definitely need to check it.
No, absolutely. I do agree with you, and that it's really fascinating. You know, there's also bioglasses with cobalt. They also see some effect. So I think there's certainly something in there. When you see that your osteoclasts were that really pure osteoclasts, because on the pictures you showed also today, I had also the impression there are still some monocytes around. Do you think they have also a role in the process?
They could have, because at this stage there should be macrophages. So the cell culture we did was we seeded CD14 positive monocytes on our membranes, and we induced them to turn into osteoclasts with rank ligands. The control condition was MCSF only, which would direct them to macrophages. And they could, for example, macrophages phagocyte particles that are loose by mechanical agitation of the substrate, for example. But macrophages are not able to resorb bone if it's, this material, if it's not really in particles. So only osteoclasts are able to both dissolve the mineral and the organic matrix as well, because they have the enzymatic components for it.
And when we then go back to the previous opponent who says we may implant it in vivo, then you have also other cell types. You can imagine that the macrophages that are then present in your material can have an effect on, and a certain effect on other cells?
I imagine so. So macrophages, they have multiple phenotypes,
exactly.
And based on the conditions induced by the biomaterial or the wound itself, they could go towards more regeneration, then influence cells surrounding them into those pathways of regeneration or more of inflammation, which would then be probably counterproducing to the healing of the wound. So they will definitely play a role in vivo.
Yeah, exactly. I think we have also seen at one time when you have M2 macrophages, osteoblasts are much more active. In chapter 5, however, you didn't choose osteoblasts, you choose mesenchymal stem cells.
Yes.
And you put it on a membrane, but again, without the cobalt. So, and there you have also the stiffness. So do you think when you would have a biomineralized, or like what the first opponent said, we should call it differently, membrane, would that make a difference when you put in cobalt for your mesenchymal stem cells? Very
good question. I think yes. I mean, depending on the concentration that is released, we had on the previous chapter, so the cobalt release was about the tens of nanomilimolar after 2 days, which is very, very low, but it could have an effect. I think struggling to see what is the effect of cobalt on HMSCs, and I think it has something to do with angiogenesis. And with cobalt, with other ions, what we managed to prove with cobalt is that we can put it in biomineralized collagen, because it's actually not that trivial, because during the intrafibrillar mineralization of collagen, it's really hard to dope it with trace ions because it disrupts the process of mineralization. So we need to do an extra step after that. Cobalt is interesting because in the case of osteoclasts, potentiates resorption. In the case of HMSCs and angiogenesis, but also other ions would be useful, in particular for HMSCs. Strontium, for example, would be good to have there for a wound healing scenario.
Yeah, absolutely. And then perhaps a last question. When we look at its cultures, you see the HMSCs, you said, okay, they have RANX2, osteopontin, they have some alkaline phosphatase you showed, but did they also mineralize?
Yes, we were able to detect mineralization on our controlled collagen samples, which didn't have the calcium phosphate mineral, just because then it's then easier to detect. Any mineral that was put there probably was by the cells. Of course, could be deposition from the medium, but we controlled for that as well, didn't see anything. On the biomineralized membranes, it was harder to detect, or we couldn't detect extra calcium phosphates. It's an ongoing challenge to detect cell-induced mineralization of substrates with calcium phosphates. There are some techniques we can use. One of them is, for example, you could label the calcium in solution, so free calcium, and then if it's deposited, if you see it with fluorescence microscopy, it could be from cell mineralization. Well, another problem is that in these membranes or any calcium phosphate containing material in medium will induce precipitation of calcium phosphate onto the membrane. So the cell mineralization needs to be above that threshold of of just precipitation from the medium, but it could probably be done. Yeah.
Okay, I'm very happy with your answers. Thank you very much, and I give back to the pro-rector.
Thank you very much, Professor van Greenstein, for your contribution. The opposition will be continued by Dr. Vanessa Laponte. She works at Merlin and is an expert in cell-material interaction in this university. Professor Laponte, please, the word is yours.
Thank you, Mr. Pro-Rector, and dear candidate, of course, I'd like to start by joining my colleagues on the Defense Committee and congratulating you and also your supervisor. Very interesting, very also interdisciplinary thesis, which I think we're seeing by the nature of quite diverse questions today. So I, of course, am interested in how the cells are responding to the materials. So I'd like to just start with a very general question, which is actually, can you just walk us through the process of when your trypsinized cells in solution first encounter these membranes? What is happening biologically with the cells and their interactions?
My esteemed opponent, thank you for your kind words for my thesis and your question. Would you just mind rephrasing it? So when you trypsinize cells from the membranes?
Sorry, the other way around. So you have a solution of trypsinized cells and you're first seeding them onto the membranes. What does the cell see? What is happening biologically there?
So the first contact with cells with our biomaterial. So what we did before seeding the cells was incubating biomineralized collagen membranes in medium. So there, I imagine, would be some protein adsorption on the surface. And so the monocytes, in the case of chapter 3 and 4, HMSCs in case of chapter 5, when they contact with the material, they would probably see these proteins that were absorbed there, but also be in contact with the collagen and calcium phosphates moieties that are around there. And yes, they will probably try to attach first and all of that.
And can you say something a little bit more about that attachment? Like, what is it at the cell membrane that is starting to engage with your material? How is this interaction taking place?
Right. I see where it's heading. So in the case of osteoclasts in particular, the attachments and also their function is tied to activation of integrins in their membrane. One integrin in particular, the vitronectin receptor. And our material, of course, it's only collagen and calcium phosphate. So collagen doesn't have any exposed RGD, for example, moieties on it. So any attachment molecules on the cell membrane, they're not binding to RGD that is present on the membrane. But osteoclasts have, for example, an integrin that is able to bind directly to collagen. So I think perhaps that is what is happening. That is how they're able to attach and spread and not proliferate, but migrate, even in the absence of a lot of RGD moieties in the membrane.
Yeah, I find that interesting you say this because yes, for sure, the cells are able to attach, so they have a receptor capable of doing so. But especially the conclusions in chapter 3 were quite strongly based on the concept that there was no engagement of, say, an RGD binding integrin. Are you really so certain that the cells didn't produce some extracellular matrix of their own in this period?
I'm not. So they could have produced matrix, but from what I read in literature, so there are two steps, of course, the attachment and the establishment of the cell on the surface, and then its function, in particular, the resorptive function. And what I saw was that there's one integrin in particular that is critical for allowing resorption to happen, that is the vitronectin receptor. But other integrins are able to allow the osteoclasts to adhere and behave normally form, actin rings even if they're not able to resort. The strong conclusions from that came from reading studies where they did very similar substrates without the mineralization, but with collagen, and where they control the composition of the medium. So they were sure there were not any proteins being deposited from the medium containing these molecules. And then they saw, for example, actin ring formation in the absence of vitronactin. But I'm not sure whether these cells could produce the matrix themselves that they would attach to. That I'm not sure.
Okay, that's interesting. Would you actually propose modifying the membrane with like RGD or with protein perhaps? How would you approach that? If
Absolutely.
You
After chapter 3, that was one of the things I thought about doing. So, and it falls in nicely with the process of building these membranes as well, because we use an analog for proteins that in bone are responsible for the mineralization of collagen, for example, osteopontin. You can replicate the same mineralization process with osteopontin and have it in this material, and osteopontin has an RGD moiety on it. So that would be one very good way to go about it and see, for example, if there would be resorption in that case without changing anything else, no stiffness, no cobalt.
Yeah, that would be very interesting. Something I noted when reading was it seems as though your line of thinking actually changed between chapters 3 and 4. I don't know if you did the experiments in the order that they're presented in the thesis, but going from chapter 3 saying that RGD must be needed to chapter 4, in fact, where it was not a strategy to do it. Can you explain a bit of why those choices were made?
Yeah, you're absolutely right in that the reasoning changed. Although the conclusion from chapter 3 was that the main reason why I thought that there was no resorption was indeed the physical chemical properties of the substrate, and not so much the presence or absence of RGDs, because they are actually in the medium, maybe not to amount sufficient to allow a lot of resorption, but a little bit. Why go for extra mineral and cobalt and not the RGD pathway? Is because of that. It's because I thought that, and I still think that physical chemical properties were the reason why there was no resorption. So I thought, okay, if we increase stiffness, if we had extra mineral, actually the goal of adding extra mineral was to reduce porosity. But we ended up discovering that all the mineral was deposited on the already mineralized fibers. So the porosity remained very much the same, even if stiffness increased. But the choice for cobalt and extra mineral came from me thinking that the physical chemical properties of the substrate were more important than the presence or absence of these biomolecules.
Yeah, okay, that's interesting to hear. The about the stiffness, of course, it's also the RGD binding integrins that might transmit that stiffness. Do you think there might be an opportunity to combine these multiple strategies into something that would be even better, or are you really certain that it's not necessary?
No, I mean, I think that activation of the vitronactin receptor is necessary for resorption. And we saw a little bit of resorption on the cobalt and extra mineral chapter. But I'm also not sure if there's vitronactin in there or not. It could be from the medium, right? And maybe that's why we have resorption. So if I would say, okay, what is your best strategy to potentiate osteoclast resorption to the maximum? Absolutely have the vitronactin there, other RGD moieties, and other signals that could induce osteoclasts to increase their activity, such as the cobalt, and in this case, stiffness as well. So just combine the three of them would be my best choice. Yeah.
And then a follow-up on it seems you're very strongly in favor of the physical chemical properties. That's okay. But a follow-up on the idea around the stiffness, the range that you tested, I mean, it was significant in the sense of from 1 to 10 megapascals, I think, difference, right? Do you think though that that's enough, or would you also say that this would be an even enhanced effect, say, going further in that direction?
So physiologically, it makes sense that it needs to be more. Woven bone is about hundreds of megapascal, so 10 times higher than what we have in the more stiffer membranes. So in that sense, it makes sense to go for higher stiffness. For example, our controls were bone slices, cortical bone slices, and we're talking in the range of gigapascal. So higher stiffness is always better for osteoclast resorption, I think.
Thank you.
Thank you.
Daniel de Melo Pereira. The time appointed for defending your thesis has passed. The degree committee will now withdraw to discuss the quality of your thesis and your defense. I request that you and your company await the results of our deliberations and our return to this room. Daniel de Melo Pereira. The degree committee has here present has assessed the quality of your thesis and your defense. In view of its positive verdict and taking into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. Professor Habibovic is authorized to confer upon you this academic distinction in the accordance to the Dutch law custom at the university. I invite you, supervisor, to now take the floor. All standing, please.
Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent, and responsible?
I do.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Daniel de Melo Pereira, the degree of doctor, and grant you all rights attached by custom and law. As evidence of this, I now present you with the degree certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university. Dr. de Melo Pereira, dear Danielle, I am very pleased to be the first to congratulate you on obtaining your PhD. A big day in one's life, something we occasionally tend to forget because we are surrounded with so many people holding a PhD. And this is a pity, because this day is a reward for many years of hard working, often with failures and disappointments, with periods of time when motivation is lacking, with questions, what am I doing and why? Obtaining a PhD is a proof of so much more than your knowledge of biomineralization or bio-inspired materials. It is also an evidence for your perseverance and your transformation from a student not really sure what to do in his life to a grown-up scientist who still may not be sure what to do in his life, but having so much more ammunition to take a right decision. Your trajectory was even a bit more complicated than an average one, to express it mildly. It actually started before your PhD, as you came to my research group at that time at the University of Twente to do research on your master thesis, an Erasmus student. You did this project very well, so well that this work resulted in a publication. This publication eventually made it to the thesis of your daily supervisor, David Barata, who I suppose is online now. But the efforts you put in that work should not be underestimated. This research project showed immediately that you are a creative, hardworking researcher, very helpful and collaborative. All ingredients that are required for becoming a successful scientist. This was the reason why I decided to offer you a PhD position. And then we started our Maastricht adventure. You accepted the PhD position and therewith also the fact that your research would be done here. But this was easier said than done. We came to Maastricht with great plans, but we also had to start from scratch. The labs had to be built, equipment purchased. This was a tough start, as it meant that for many months, no experiment could have been done. It required, again, patience. Once you could start, you had a very explicit idea about what you would like to do. I was interested in biomineralization and how to use it in bone regeneration, more from a material science perspective, but you chose to look at it in the context of osteoclastic resorption, as we have seen today. Today, I wonder if you regret it. Osteoclasts, especially derived from monocytes from human blood, turned out to be very difficult to work with and control. Indeed, a big part of your PhD time you spend making those cells do what you want them to do in order to be able to perform actual experiments. This was frustrating for sure, but it again showed your endless patience and perseverance. And due to this, you have a thesis to be proud of, with a very insightful review and 3 research papers published. We sometimes used to joke that the largest part of your thesis should consist of things that did not make it to a paper, as they did not work out, could not be finalized, etc. I actually had to convince you to add the behind the scenes chapter to your thesis to demonstrate how much work you have actually put into it, but also to allow others to learn from the experiments that did not work. I believe that we should do this more often in science. Besides your own work, you were so often the go-to person for all kinds of questions and help in the lab. This is reflected in 7 papers by your colleagues that you co-authored. But you did so much more that can be seen in these co-authorships, simply because of your humbleness and your answers like, oh, I just helped out. It's certainly not enough to justify a co-authorship. In a system that unfortunately still is based on a publish-or-perish struggle, you gave an example of what true team science is. And that is what I appreciated the most in you. But there are so many things, more things to value in you as a scientist and as a person. Your always positive attitude, your creativity, your honesty, even when things do not go the way you would like them to go. And also your ability to claim freedom to do research you want to do in your own way without being stubborn or disrespectful to others. I often said that you are a person one cannot get angry with, regardless of circumstances. I certainly could not. And I always enjoyed every interaction with you. Dear Danielle, you are a doctor now and a bright future lies in front of you. You are not sure how exactly this future will look like, but I'm sure it will be great. You will climb those boulders, mountains, challenges, but not only to reach the top, but to enjoy the view on the way. And that is what is typically Danielle for me. Now, before I close, I would like to thank your assessment and promotion committee, the chair, Professor Zeider, Dr. Akiva, Professor Klein, Professor van Greenstein, and Dr. Lapointe. And also let me embarrass myself again in Portuguese to congratulate your parents who had to miss their only child for so many years while he was enjoying the academic life. Parabéns, espero que desfrutem deste dia especial. Tem todos os motivos para ter orgulho no Daniel. Dear Daniel, congratulations again. Enjoy this moment, this day, and let's make sure that we celebrate with IB and Marilyn as soon as we can. Thank you.
Thank you very much, Pamela, for your great presentation. Dear Dr. Melo Pereira, also on behalf of the Board of Deans, I congratulate you with the honor you have acquired. And I know you already for many years. You were the first PhD candidate coming to our new microscopy laboratory core facility to do microscopy. And you have been doing great work, and all my colleagues have been enjoying collaborating and interacting with you, and they want to bring the congratulations also to you. They were unable to attend here live, but they do like me to transmit congratulations. Also, I like to congratulate the parents for your son who got now a doctorate degree. He did a really good job. I did bone research myself during my undergraduate in biomineralization of the bone in Utrecht, and I was able to understand your talk very well. Your questions and answers was enjoyable for me, I hope that you have a good future. Make good choices. As Pamela said, you are prepared for going to the next step, and I wish you good luck, also on behalf of the university. And I'd like to thank also on behalf of the university all committee members for evaluating the thesis and for participating in this defense. The official ceremony is by this closed, and we go on for a group picture in which we keep the COVID restrictions of